Hey guys, and welcome back to this video. Today we're going to learn how to draft polynomial functions using the y-intercept, the x-intercept, also known as the zeros, and their multiplicities. Let's go. Hey guys, and welcome back. If you've not done so yet, go ahead and subscribe to my channel so you can get more content like this one. Today I'm going to be talking about how to draft polynomial function. Now to begin with, a polynomial function is a function that's written in the form f of x equals to an x to the power of n plus an minus 1 x to the power of n minus 1 plus dot 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 plus a2 x to the power of 2 plus a1 x to the power of 1 plus a0 x to the power of 0, where an is not 0. Alright, and so if you would like to know more about what polynomials are, I recommend that you check out my note 4, where I talk just about that. Okay, so to draft a polynomial, we're going to be looking at a few things. We're going to be looking at the end behavior of the function. We're also going to be looking at the multiplicity of the zeros, also known as the x-intercept, and we're going to look at the y-intercept as well. For the end behavior, it is determined by looking at the leading term. In my general formula here, given that an is not equal to 0, my leading term would be an x to the power of n. And so, looking at your leading term, if you have a function that has a degree that is even, for instance, n equals 2, then the end behavior of the function will be going in the same direction, as you can see in my example here for n equals 2. On the other hand, if you have a degree that is odd, then the end behavior of your function will be going in different direction, as you can see in my example here for a polynomial of degree 3. Okay, so other than that, if you look at the leading coefficient, an, when the leading coefficient an is bigger than 0, positive, it means that your right end behavior will be going up to infinity as x gets bigger. And when your leading coefficient an happens to be negative, it means that the right end behavior will be going down, meaning as x goes to infinity, your function will be going to negative infinity. And that will be the exact same thing with an odd function. So if you have a leading coefficient that is positive, your function will be going up on the right side. And if your leading term is negative, your function will be going down on the right side. And so the combination of those two, the leading coefficient and the degree, should tell you what your end behavior look like, the right and the left. Because if your leading coefficient is positive, the right will be going up, and so if your function is even, so the left. If your function is odd, the left will be going in the opposite direction. But if your leading coefficient is negative, the right will be going down, and so if your function is even, the left will be going to the same direction, down, and if your function is odd, it will be going in a different direction, meaning up. And so with that, you should know that a polynomial has a max number of turning points equal to n minus 1. As you can see here in my example where n equals to 2, I only have one turning point. And in my example where n equals to 3, I only have 2 turning points. Alright, so let me give you some examples so you can see how that comes to life in practice. So if I give you the function f of x equals to negative x to the power of 4 plus x to the power of 2, then your leading coefficient here is going to be an, which in this case is going to be negative 1, which means that your right end behavior would be that the function goes down to infinity. And since the function happens to have a degree of 4, which is even, the left will be behaving the same way as the right. And so you're going to have both the right and the left end behavior going down to negative infinity. Next, the y-intercept here will be found by setting x equal to 0. And so if you do that here, you will get that y is also equal to 0 by plugging into the function f of x. Because you would have f of 0 equals to negative 0 to the power of 4 plus 0 to the power of 2, which equals to 0. And for the x-intercept, or also known as the zeros in this case, you would want your y coordinate to be 0. And so in this case, we're going to have negative x to the power of 4 plus x squared equals to 0. And to solve this particular equation, we're going to have to factor the polynomial. And if you want to know more about how to factor polynomial, I recommend that you check out my note number 5, where I talk about that. So in this case, if you look at your polynomial here, you're going to notice that the factor negative x squared is common to both of our terms. And so if you take negative x squared out, we're going to have negative x squared, and in parentheses, we're going to have x squared minus 1 equals to 0. And so that will give us negative x times x and x minus 1 times x plus 1, because that's what the difference of square gives you, equal to 0. And so from here, we can see that x will be equal to 0, or x will be equal to 0, or x should be equal to 1, or x should be equal to negative 1. The multiplicity is the number of times a 0 happens. So in this case, since x equals 0 happens twice, we're going to say that x equals 0 has a multiplicity of 2. And so x equals 1 will have a multiplicity of 1, and x equals negative 1 would also have a multiplicity of 1. Once you're done with this, you can go ahead and draw your plane so that you can draw your function. So I'm going to do that here very quickly. And then once I'm done with that, I'm going to go ahead and take everything that I've learned about the polynomial and plug them into my graph. And so first thing first, we're going to go ahead and put all our intercept point on the graph. And so we're going to have the point of coordinate negative 1, 0 here, and then the point of coordinate 0, 0, and then the point of coordinate 1, 0. After we're done with that, you're going to keep in mind that your end behavior on the left and on the right should be to negative infinity. And so looking at the multiplicity here, what the multiplicity is telling you is the behavior of the function as you get closer to the 0. And so when you get close to the 0 here, the function is going to behave like the basic function x to the power of whatever multiplicity you have for that 0. What I mean by that is, for x equal negative 1 here, since that's the multiplicity of 1, as you go close to negative 1, you're going to have to cross negative 1 as a variant of the basic function y equals x. So I'm going to have a little line here that looks like a y equals x function. And then when I get to x equals 0, since that has a multiplicity of 2, I'm going to go ahead and draw something that looks like a parabola here because that's x squared. And then if I get to x equals 1, I'm going to go ahead and draw something that looks like a variant of y equals x. So in this case, it's going to go like this, since our function is to go to negative infinity, as the end behavior tells us. Once you have the zeros down and the behavior close to the 0 drawn, keeping in mind the end behaviors, you can go ahead and connect all these points so that you can get the graph of your polynomial. And as you can see here, the maximum number of turning points is, in fact, 4 minus 1, which is 3. So you can see clearly here that we have 1, 2, 3 turning points, and you will be done. All right, so let me give you more examples so that you can get this concept just, sink in. Our second example here is going to be the function g of x equals to negative 3 x to the power of 3, in parentheses, x minus 1 squared, in parentheses, x plus 3. And so this particular one is not written in a general form, it's written in a factored form, which means it's not going to be as easy for us to read out the leading term directly, but on the plus side, it's going to be easier for us to find the zeros. So our leading coefficient here is going to be found by multiplying the leading coefficient of each of the factors that are making up the polynomial. So for the first factor here, we're going to have that our leading coefficient is going to be negative 3 times. The second factor here has a leading coefficient of 1 squared because the whole factor is being squared, times the last factor here happens to have a leading coefficient of 1. And so if you multiply all of these through, you're going to get that our leading coefficient for the function g of x is going to be negative 3. For the degree, since the degree is a power, you're going to have to add the power of all the factors making up our polynomial. And so the first factor here has a degree of 3, plus the second factor here inside has a degree of 1, but it's squared, so you're going to have 1 times 2, plus the last factor here has a degree of 1. And so finally, you can add all of these degrees up, and you will get that the degree of the function g of x is equal to 6. So with a combination of these two, the leading coefficient and the degree, since the leading coefficient is negative, that means that on the right, the function will be going down to negative infinity. And since our degree is even, it means that on the left, the end behavior will be the same as the right. Okay, since that's done, we can go ahead and figure out our y-intercept. And so for that, we need x to be equal to 0, which means that y will be equal to g of 0, which is equal to 0 times negative 1 squared times 3, coming from all three factors that we have above. Multiplying all of these two will give us that the y-intercept is equal to 0. Alright, and for the x-intercept, or also known as the zeros, we need y to be equal to 0. And so if that's the case, we need to find the x value that will make the function g of x equal to 0. And to do that, since our function is already factored, we can just read off what will make each of the factors equal to 0. So for the first factor here, x should be equal to 0. For the second one, x should be equal to 1. And for the third one, x should be equal to -3. And of course, the first one here has a multiplicity of 3. The second one has a multiplicity of 2, and the third one has a multiplicity of 1. Once you've done with finding all of these things, you can go ahead and draft this particular polynomial. And so let's go ahead and do that here. First, we're going to go ahead and plug all our intercepts. So we're going to have the point of coordinate -3, 0, then the point of coordinate 0, 0, and finally 1, 0. Once you're done with that, you're going to keep in mind that your end behavior on the left and the right are going to be that the function should be going down. And so when you go towards the 0 at -3, you should know that you should pass the 0 as a variant of the function y equals x. And when you get to the 0, x equals 0, you should know that since the multiplicity is 3, you should pass the 0 as a variant of the x cubed basic graph. And so that's going to look like this. And finally, when you get to 1, you're going to bounce off as a parabola would. And so once you have all of that done, you can now go ahead and connect all of these points, keeping in mind the end behavior and the behavior of the function next to the zeros, and you should be done. Also, as you can see here, since our degree is 6, we should have a maximum of 5 turning points. And as you can see on this graph, we have 1, 2, 3, 4, 5 turning points, and that checks out. Okay, so let me give you one last example. We're going to have the function h of x equals to -2x squared, in parentheses 5x minus 2 to the power of 3, in parentheses x squared plus 1, everything to the power of 2. Then we're going to do as we did before. For the leading coefficient, we're going to have to multiply the leading coefficient of each of the factors making up the polynomial. And so our first factor here would have a leading coefficient of -2, times our second factor here would have a leading coefficient of 5, and that's going to be cubed because the whole factor is being cubed. And finally, our last factor is going to have a leading coefficient of 1 squared because the whole factor is being squared. And so multiplying all of these things would give us -2 times 125, which is going to be equal to -250. Okay, next we're going to look at the degree. And again, to find the degree of polynomials that are written in the factored form, you have to add up the degrees of all the factors. And so our first factor here is going to have a degree of 2. Our second factor here, the inside has a degree of 1, and since that's cubed, that's going to be 1 times 3. And our last factor here has a degree inside of 2, and since that's squared, we're going to have a degree of 2 times 2. And we can go ahead and add all these up and get that the degree of the polynomial h of x is equal to 9. And so what that means is, since the leading coefficient is negative on the right side, the end behavior will be going down to -infinity. But since our degree is odd, the end behavior of the left side will be opposite or at odds with the end behavior of the right side. And so we're going to have that our function will be going down on the right, but up on the left. Next, our y-intercept is going to be the point of coordinate x equals 0 and y equals 0, because when you plug in x equals 0 into the function, you just get 0. And for the x-intercept slash the zeros, we need our y coordinate to be 0. So if you want the polynomial h of x to be equal to 0, we would need at least one of its factors to be 0. And so we're going to have -2x squared equals 0, which means that x should be equal to 0. And that's going to have a multiplicity of 2. Next, we're also going to have 5x minus 2 to the power of 3 equals to 0, which means that x should be equal to 5 divided by 2. And that's going to have a multiplicity of 3 because the whole factor is raised to the power of 3. And the last one here, x squared plus 1 squared equals to 0, would mean that x squared should be equal to -1. And as we know, that is impossible because as you take the square root of both sides, you don't want any negative number under the square root because that x value would not be real. And so in this case, the 0 does not exist, or more specifically, it's not real. It's complex, and we are not dealing with complex numbers right now. So once you're done with figuring out all of these things, you can go ahead and start plugging those points into your graph. And so I'm going to have the point of coordinate x equals 0, y equals 0 here. And I'm going to have the point of coordinate x equals 5/2 and y equals 0. So those are all my zeros. And so keeping in mind that my function's end behavior on the left should be that the function goes up to infinity, and on the right should be that the function goes down to a negative infinity. I'm going to keep in mind that on the left here, I'm coming from positive infinity. And so when I get to 0, my graph should behave like a parabola because 0 has a multiplicity of 2. And then when I get to 5/2, my function should behave like a cubic function, like an x cubed function. And so once I have these things done, I can go ahead and connect all these points, keeping in mind the end behavior and the behavior at the zeros. And so I'm going to have a graph that looks like this. And that would be done. Also, keep in mind that in this case, our maximum number of turning points is going to be 9 minus 1, which is 8. And as you can see here, we do not have more than 8 turning points. So that's good too. All right, so we are done here. As usual, if you would like a PDF copy of this note, check out the descriptions below. And next time, I'm going to open a brief parenthesis to talk about the intermediate value theorem for polynomials. And if you like the way I break down the material, give me a thumbs up, and I'll see you then. Bye.